Now let's look more closely at some of the properties of water. Water is actually an extremely weak electrolyte, meaning that when it exists, it actually forms some ions. Water will actually form all by itself H plus and OH minus, acting as if it were an ionic compound even though it's molecular. Water has a very, very small concentration of these two ions. In pure water, these concentrations are equal to one another, and they are both equal to 1 times 10 to the minus 7 molarity at 25 degrees Celsius, which is a very, 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 very small concentration. When we take the concentration of H plus and multiply it by the concentration of OH minus, it equals 1 times 10 to the minus 14th. This is what's known as the ion product, or Kw. And anytime you have a solution where the solvent is water, the concentration of H plus times the concentration of OH minus must equal this value. So if we're not looking at pure water, this still has to be true. So for example, if we have an acid solution, we add an acid to water, which means our H plus increases, then our hydroxide must decrease, because when I multiply these two values together, the concentration of H plus times the concentration of OH minus, it must always equal this value. So, when the concentration of H plus is equal to hydroxide, they are both 1 times 10 to the minus 7. That's what's known as a neutral solution. Acidic solutions have concentrations of H plus higher than that of hydroxide. So the hydrogen or the proton concentration is going to be greater than 1 times 10 to the minus 7, and the hydroxide concentration will be less than 1 times 10 to the minus 7. If we look at basic solutions, our hydroxide concentration will be larger than 1 times 10 to the minus 7th, but our hydronium concentration, or our proton concentration, will be less than 1 times 10 to the minus 7th. Okay, so let's determine whether each one of these is acidic, basic, or neutral. If our concentration of hydroxide is 2.5 times 10 to the minus 4th, this is greater than 1 times 10 to the minus 7th, so this is basic. Here, 3.5 times 10 to the minus 8th is smaller than 1 times 10 to the minus 7th, so this is acidic. Here, our concentration of calcium hydroxide is 0.2 molar, which means our hydroxide concentration is 0.4 molar, which is definitely larger than 1 times 10 to the minus 7th, so this one is basic as well. So, base, acid, base. And the authors of the slide went through and did the math to calculate the concentration of hydronium, but we didn't need to do that. We could figure out whether it was basic or acidic just based on its hydroxide concentration. Now, dealing with these very small concentrations can get kind of tedious. So we have what's known as a pH scale, which allows us to describe the acidity or basicity of a solution in numbers that we're more familiar with, basically from 0 to 14. This is the definition of pH. pH is equal to the negative log of our proton, our H plus, or our hydronium. And what a log is basically just an exponent. So let me show you how this works, and I think the pattern will be a little clearer. If our pH is 0, our concentration of H plus is 10 to the 0, which is equal to 1. So therefore, our concentration of hydroxide has to be 1 times 10 to the minus 14th. Because when we multiply these two concentrations together, they have to equal 1 times 10 to the minus 14th. If our pH is, where's my pen? If my pH is 1, my H plus concentration is 10 to the minus 1, which is 0.1, which means my hydroxide concentration is 1 times 10 to the minus 13. If my pH is 2, my concentration of H plus is 10 to the minus 2, which is 0.01, which means my hydroxide must be 1 times 10 to the minus 12. If my pH is 3, it means my concentration of hydronium or proton, is equal to 10 to the minus 3. So that means my concentration of hydroxide is 1 times 10 to the minus 11. If my pH is 4, my proton concentration is 10 to the minus 4, and my concentration of hydroxide is 10 to the minus 11. 10 to the minus 10, sorry. If my pH is 5, my concentration of hydronium is 10 to the minus 5, and my concentration of hydroxide is 10 to the minus 9. If my pH is 6, my concentration of hydronium is 10 to the minus 6, and my concentration of hydroxide is 10 to the minus 8. If my concentration is 7, if my pH is 7, the concentration of proton is 10 to the minus 7, and that of hydroxide is 10 to the minus 7. So here we're at neutral. If my pH is 8, the concentration of hydronium is 10 to the minus 8, and my concentration of hydroxide is 10 to the minus 6. If my pH is 9, the concentration of hydronium is 10 to the minus 9, and hydroxide is 10 to the minus 5. So as my pH goes up, my concentration of my acidic component, my hydronium or my H plus, goes down. And once we know our concentration of hydronium, we can calculate our concentration of hydroxide, because when we multiply these two together, they always have to equal 10 to the minus 14th. So, even though the pH gives us values that we can deal with, usually between 0 and 14, it's a little confusing, because as pH goes up, the concentration of hydronium goes down. So here's our pH range. Below 1, very acidic, up to here at 14, strongly basic. We can have pHs greater than 14 or less than 0, but typically we don't. They're usually within this range. And 7, we have equal concentrations of H plus and OH minus. That's neutral pH. And here are some pH values of some common substances. Hydrochloric acid, if it's 1 molar, has a pH of 0, 0.1 molar, a pH of 1. Stomach acid has a pH between 1 to 3. Lemons, 2.2 to 2.4. Soft drinks, 2 to 4. Plums, apples, cherries are all acidic. Most foods are in the acidic range. Unpolluted rainwater is actually acidic. Blood is a little bit basic, as are egg whites. These are one of the few foods that are actually basic. Milk of magnesia, 10.5. Household ammonia, 10.5 to 11.5. And then lye or sodium hydroxide drain cleaner would be in this range as well. This 1 molar sodium hydroxide, which is drain cleaner, would have a pH of about 14.